Okay, hello, environmental science. Today, we are talking about Earth's spheres, as you probably got from the assignment name on Canvas, which is essentially just how we divide up the way the Earth exists and the systems that exist within it. By the end of today, I want you guys to be able to describe the geosphere, atmosphere, biosphere, and hydrosphere, as well as be able to tell me how they all connect with one another. So, you will have to take notes over this. So, hopefully, you have your notebooks with you. If not, find a piece of paper, take notes on it, and you can paste them into your notebook whenever you get your notebook. So the way I have, you can take notes however you want, but the way I've divided up my page so that everything fits on it is like this. Um, so this information will come in handy again and again and again and again, especially because we will have an assessment over this unit when it is done, and it is much longer than our last unit. So you will need this stuff in the future. Also, you learn better by writing, as I will say over and over and over again. It may help to have a couple different colors. I know it helped me, especially when we talk about the geosphere. Um, so this is how I divided it up. We've got, I just cut the page in half. And because the geosphere has the most information on it, and then we've got the atmosphere and biosphere down here. The biosphere is literally just a sentence or two. And then here is the hydrosphere. You might need to go onto the second page for the hydrosphere because we talk about the water cycle in it. But overall, this is how I was able to do it. But just take notes however you want. But this is how I organized it. So, when we talk about the geosphere is essentially all of the rocks and minerals on the Earth's surface, um, as well as all of the rocks that are below it. Geo, rocks, sphere, because the Earth's a circle or a sphere. Um, so what I do want you to have in your notes is essentially this cross section right here. You've probably drawn it a bunch in a lot of different science classes, but just we've got the Earth's crust, we've got the mantle, we've got the outer core, and we've got the inner core. So the crust is all of that cool rock that forms the outer skin of the Earth, and it is both the land and the oceans. So the oceans are a part of the geosphere. Then we've got the mantle, which is solid hot rock. And just because it's solid doesn't mean necessarily that it's all like stuck together and like bedrock. The mantle, parts of it are kind of like if you've ever played with like moon sand. So that's a solid, but it can move around and stuff. So that will come in handy in a minute when we talk about the asthenosphere. Um, so the crust is that cool layer. The mantle is all solid hot rock. The core has two parts. The outer core is molten metals, and the inner core is solid metals. So we've got the inner core being solid metals. We get the outer core being liquid metals. Then we've got our solid mantle and our oceans and land crust. But there's two more divisions that I do want you to have. So if you can fit these labels in your drawing over here, that's fine. If you want to have a separate drawing for it, that's cool too. So the lithosphere is made up of the crust and the upper mantle. So the mantle can be divided into the upper mantle and lower mantle. So the lithosphere is the crust and this upper mantle, and the asthenosphere is the portion of the mantle just below the lithosphere. So if we've got this upper mantle right here, the lithosphere is the crust and this uppermost part of it, and the asthenosphere is just another layer in there that has a lot of that kind of like moon sandy-ish acting rock. So that's how the geosphere is divided up. and it's important to know these divisions for stuff like tectonic plates. So, tectonic plates are just large portions of the lithosphere that float on the asthenosphere. So, all of Earth's lithosphere can be divided up into these plates like this. So that's a plate, that's a plate, that's a plate, that's a plate, etc. And they all float on that asthenosphere. And every single year, they move about 2 to 15 centimeters, depending on how active like fault lines have been. Um, but essentially, every year, 2 to 5 centimeters, these plates move around. At least twice in all of the world's history. So, since the Earth became the Earth, at some point these plates have aligned to where all of the land on Earth, so all of this stuff, has connected into one giant continent called Pangea. And then it broke apart, the plates floated around a little bit and then it came back together and then it broke apart and then they all spread out to where they are now. So if you can kind of see, like, we've got Africa right here, it could fit technically in this little space right here. And they all just, and same with, if we look at Australia, that could come up here. And then that just comes together to form what we call Pangea. And what we're really interested in when it comes to plate tectonics is these lines, these places where the plates meet. And there are a couple different boundaries. So, when plates move and slide, they create landforms. And there are 4 different boundaries that I want you guys to have kind of doodled in your notebooks, just so you know the difference between the two and the names that go with them. So over here we've got a divergent boundary. So sometimes the plates go away from one another. That is called a divergent fault line, and essentially that can form like chasms and stuff, but also magma that is floating down here. So if you go back to this line right here, so at this plate boundary right here at the bottom of the ocean floor, there's a divergent plate boundary. And essentially what happens is all of the magma and molten rock that has come up down here will fill up these cracks and we'll get more land and more land and more land. But when I say land, I just mean more ocean floor. So we're technically creating more surface at the bottom of the ocean with these plates going across from one another. We also have transverse fault lines where they kind of slip across one another, transform. Yeah. So one goes one way and one goes the other way. I'm making hand motions. You can't see them. I will try to use my camera in the future. So these plates are going away from each other this way. When this happens, there's a lot of friction right here, and that can cause earthquakes. So the San Andreas Fault, I believe, is either convergent or transform, and it's what causes a lot of earthquakes in California. And then we've got convergent, so when the plates come together, and there are 2 ways convergent boundaries can form. So sometimes when they get pushed together like this, one of them slips under, and then this stuff all kind of gets chopped up into the asthenosphere, and this one just keeps going over this one, and that's one. And another one is when we have uplift. So this uplift will push some of the land up and some of the land down, but this is how we get mountains, essentially. All mountains are usually formed on places that are plate tectonically active. So we get this crust coming together, crashing up, and then building up, or slipping under and going down. So that's essentially how these plates form and move. Like I said, if you have to pause it to kind of get these little drawings in there. They don't necessarily have to be 3D, just however you can get the point across that divergent plates go away from each other. Transform, they go like vertically, like against one another, creating a lot of friction. And convergent can either slip under one another or build up from one another. So that's essentially all we need to know about the geosphere. The next one we're going to talk about is the atmosphere. So the atmosphere is probably one of the spheres that we talk about the most, just because it is at the forefront of a lot of scientific conversation right now. So the atmosphere is essentially all of the gases that support and protect the biosphere. And we'll talk about the biosphere in the next slide. So this is essentially the composition of the atmosphere. You don't have to draw this, but know that the atmosphere is about 78% nitrogen and 20% oxygen. And then a bunch of other stuff that we have pumped into it or has existed from star stuff. So nitrogen takes up about 78% of the air that we breathe. Oxygen is the other 20%, and argon is over here at about 1%. So most of the oxygen that exists in the atmosphere is O2, or two oxygens bonded together. But there is another form of oxygen that exists in the atmosphere, and that is called ozone. Ozone is 3 oxygen atoms, so it would be like 1, 2, 3 oxygen atoms combined together, and its job is to protect from the sun's radiation. So the sun is very radioactive, and if we didn't have the atmosphere, A, we wouldn't be able to breathe, B, there would be nothing that would really help us stick to the earth, and C, we would all die of radiation poisoning if we didn't have something to protect us from those sun's rays. So ozone kind of deflects some of that radiation back into the atmosphere. There was a big movement, I think, in the hole in the ozone layer was a really big idea that existed, I think, in the 80s, where scientists were measuring the amount of ozone in the atmosphere, and it was decreasing, essentially, and letting more radiation in, because these greenhouse gases and other things were going into the atmosphere and reacting with it and kind of depleting the amount of ozone that existed. Luckily, we were able to kind of take action and stop the depletion of ozone, so we're good there, but now we have to deal with greenhouse gases. So greenhouse gases are essentially gases that exist in the atmosphere that trap heat and keep Earth warm. Now, some greenhouse gases is good. We like some greenhouse gases, but too many of them and the Earth starts to heat up beyond where it is supposed to be. And we will talk about greenhouse gases in the future quite a bit, and we'll talk about the greenhouse gas effect quite a bit. But essentially, the atmosphere is made up of gases that support and protect the biosphere from the sun's radiation, and keeps the Earth warm. That's all you really have to have on there. If you look at the atmosphere from space, it kind of looks like this blue, light blue kind of haze. And that's essentially the atmosphere. From the atmosphere, we are going into the biosphere. Again, you don't have to have this picture, but it might be nice to just visualize it. The biosphere is essentially living Earth. So the part of the Earth in which living things interact with non-living things. So everything from the atmosphere to the top of the crust to our soil, that is all stuff we interact with on a daily basis. So life on Earth doesn't really dig down too deep into the mantle, and it definitely doesn't reach the core, but the core and the lower mantle are part of the Earth, but they're not part of the biosphere. The last sphere we're going to talk about is the hydrosphere. So as water cycles through the lithosphere, biosphere, and atmosphere, sorry, my dog's being a little bit crazy. Anyway, as water cycles through the lithosphere, biosphere, and the atmosphere, we're able to kind of keep track of it. So most of the Earth's water is salt water. So like 97.5% of water is, 97.5% of water is salt water. So that's where we get like oceans, and that's usually not usable for the things we use water for, and it's really hard and really expensive to get the salt out of water. So most of Earth's water is salt water. So if 97.5% of water is salt water, that means only 2.5% of water is fresh water, and over 3/4 of that fresh water is stored in ice. So we only use like less than 1% of the Earth's fresh water, which is why it is so important that populations all over the world have availability to fresh water, and why it is considered such a limited resource. So I talked about how 3/4 of fresh water is stored in ice. All of the ice parts of the Earth are called the cryosphere. So this picture right here, this is land, but if you look through here, all of this, and then it's like a bunch back here, all of this is all ice. That is a glacier, a melting, retreating glacier in Iceland. That I actually got to hike on, so I took this picture. But this is just an example of what the cryosphere would be considered as. So all of this is just ice and snow. So all of our glaciers and ice caps are considered part of the cryosphere. Now, we wouldn't be able to talk about the hydrosphere without talking about the water cycle. So, this is the water cycle that you are probably most familiar with. We've got our condensation, if we start down here, we've got our evaporation, so water turning into gas, our condensation, where gas turns back into water, where it builds up in clouds until it eventually falls, gets collected, and evaporated back up. And that's the water cycle that people usually think of, but that is not the water cycle we are going to talk about. The water cycle we are going to talk about looks kind of like this. So I want some sort of water cycle drawn in your notes with all of these phrases. You don't necessarily have to have these definitions, but I do want this kind of stuff put into your notes just so you have it. So we're gonna start down here with our ground, or like lakes and oceans or whatever. So through infiltration and percolation, water gets from the surface of the earth down into the bottom of the earth, and that is considered groundwater. I don't know why that keeps popping up. Groundwater is essentially all of the water that exists underground, and a lot of this is in aquifers. So aquifers are just layers of rock and soil that hold groundwater. It's not necessarily like underwater lakes. It's kind of like if you're at the beach and you dig into the sand and you get so deep that every time you scoop sand out, water just kind of fills it up because that sand was holding that water. That is kind of how aquifers work on like a massive scale. So here we've essentially got what our normal water cycle would look like. We've got oceans. They evaporate water from liquid to a gas. It comes up into clouds where it is condensed to form a liquid and then precipitated back onto the earth. And that's essentially the water cycle that we're used to. But we're going to add a couple things to that cycle. And one of those things is transpiration. So this groundwater plants take up, And transpiration is essentially the release of water vapor by plants through their leaves. And you would think that this doesn't take account for a lot of the water cycle, but it really, really does if you think about the amount of trees and plants that exist in jungles and forests and all that stuff. So transpiration is the release of water vapor by plants through their leaves. So transpiration gets water into the atmosphere again. It condenses. We've got this process of transportation, which is essentially that the atmosphere can carry water over really, really long different distances. And then precipitation, where water can be deposition and sublimation are essentially the water cycle, but with ice. So sublimation is getting straight from ice to a gas, which doesn't happen very often, and deposition is going straight from gas to ice. And then that water can, of course, melt and get and run off back into our rivers and lakes. So that is the water cycle. I know it looks like a lot, but it's essentially two big circles. If you think about it, one through oceans and air, and the other through plants and mountains. So if you have any questions about any of this, please let me know. Do not be afraid to send me an email. I'm here for you regardless. Make sure that you answer the questions and upload your notes like the assignment says. And I will see you soon.